everybody. We're finishing off the section or the unit on the normal distribution and the central limit theorem with one more section, the central limit theorem for proportion. So up to this point, when we've been dealing with the normal distribution and z-scores and the central limit theorem, it's all been about the mean. Every problem that we've been dealing with has to deal with the mean. We've been given a mean and a standard deviation, a mean, a mean, a mean. But that's not the only variable that we can study. So proportions are another variable that we can study. And we've seen some proportions already, but let's look at it a little bit more. So proportions are used to study qualitative data. Okay, that then is not as bright as I thought it was. Let me see if I can find a brighter one. So we've been talking a lot about numbers here. You know, we had like the mean weight or the mean consumption of meat eaten. We talked about the decibels of a cockatoo scream. We've talked all of this stuff about numbers, but there are other variables that we can study, like qualitative data, meaning like hair color or the type of trees that you have or the type of dog breeds, not how many dogs you have, but the type of breed. So in order to do that though, we can't use the mean. It would be weird to say, what's the mean tree? What the heck does that mean? Or what's the mean car color? Again, doesn't mean anything. So what we're gonna do is talk about proportions. So we're gonna say what proportion of trees are oak trees? What proportion of cars are yellow? So we're taking the qualitative, the categorical data and looking at it as proportions of the whole. And like I said, we've seen this before when we were in our probability section. So examples like this, 67% of toenails get fungus. Again, made up world, I'm just making up examples. Do not be going and telling people this is what you think, okay? I'll let you know if any of them are real. So 67% of toenails get fungus. Another one would be 12 out of 65 people eat snails. So what we're talking about is the proportion of people that eat snails. So eating snails is the variable. That's not a number, okay? It's not how many snails are you going to eat. It's do you or don't you eat snails. It's do your toenails have fungus or don't they have fungus? So again, qualitative variables, so we are going to look at proportions or percentages. Now, let's just be very clear on our variables. Again, some of these variables we've seen before, but we want to be very, very clear here. So we've got both for a population and for a sample. So the population variable for proportion is just that lowercase p. So remember, that's a lowercase p, and we find it, if we need to, by going f over n. And with every p comes its little q, and q is just its complement. So q is 1 minus p. So remember when we were doing binomial probability, we definitely saw that there, or geometric probability, where we had p's and q's going on in the same problem. Now, if it's a sample, it's going to be a p hat, but it's still going to be f over n. So we're just putting a little hat on top of the p, and that means the q will also have a little hat on him, and q hat will be 1 minus p hat. Now, the other thing to keep in mind here is how many decimal places you should use. In this example, they've said 67% of toenails get fungus. Now, the assumption there is that they mean of all toenails, okay? There's no like sample or anything. So what they're saying is P would, let me write it up there. P would equal 0.67, okay? Okay, that's the only information we have, so that's what we go with. Now in this one, it says 12 out of 65 people eat snails. Now, are there more than 65 people in general? Yes. So we're gonna say P hat, because it's a sample. But this time, we have to actually create it ourselves. So we need to do the little division problem, 12 out of 65. And when we do 12 out of 65, 12 divided by 65, I get 0.18 and then round to 5. Now notice, 3 decimals. If you aren't given 3 decimals, then you just go with what you're given. But if you actually do the calculation, that must carry that 3rd decimal place with it, okay? So 3 decimal places on that. Very important with the rounding. Okay. So again, instead of seeing problems that talk about the mean and the standard deviation, we're gonna see problems that start talking about the proportion or 12 out of 65, so proportion problems going on here. But we need to test for normal. Okay, so if we're going to use the normal curve, the central limit theorem, which applied to the normal curve, for proportions, we need to test to make sure things are normal. Now, if it was the mean, we wanted our sample size to be greater than 30, right? If we're studying the mean, sample size greater than 30 works for us. If we're studying proportions, it doesn't work quite the same way. So the test here, instead of just n, it's n times p times q needs to be greater than 10. Okay? N times p times q needs to be greater than 10. So it's different than the regular central limit theorem. Okay? But along with this test for normal, n times p times q, which we'll see in a minute, we also get a new z-score. So we can't be using a z-score that has means and standard deviations in it because we don't have any means or standard deviations running around in these problems. We're going to have p's and q's. So our z-score is definitely going to change. And this is what it's going to look like. So z equals p hat minus p all over the square root of p times q over n. Okay. Now I know at first glance you go, oh crap, that looks so much uglier than any of the other ones that we're doing. But in actuality, this big square root on the bottom is actually easier to plug into your calculator than like the big z-score that we were working with last time. And because of that, I have students that like to call this guy easy peasy, okay? So it's actually an easy z-score to calculate, okay, once you get in the habit of it. So easy peasy here, right? Okay, so what we need to do is see an example and do our test for normal, use our new z-score, and then see how this is all going to play out. And once you get used to the test and the new z-score, you're going to see the rest of it. It's just the same as what we've been doing in the last couple sections. So let's use that toe fungus one that I made up. So 67% of toes have fungus. In a random study or random sample, of 320 toes, find the probability more than 70% have fungus. Okay. So as we look at the problem, there's a sample And there are a couple percentages running around there, but there's no mean and there's no standard deviation. So there's no way that we're gonna be able to put this information into our standard big Z-score. It's not gonna work. You can try all you want, but because of the percentages, it means we're gonna have to rely on this information over here. Now, notice that it doesn't say anything about being normal. So if we want to be able to do this problem using our normal curve, then we first need to test for normal. So we need to do n times p times q. Now remember, in the statement, you're going to be given kind of an overall number. That is going to be your p. Even if it doesn't say population, this given statement is your p. So we know that p is going to be 0.67. We also need q, so if p is 0.67, q is going to be the complement, which would be 0.33. And we also have our n of 320. So we're going to take 320 times 0.67 times 0.33. Stick that into your calculator, and I get something like 70.8. Really, how many decimals you go on this, it does not matter, because all we need to know is that 70-ish is bigger than 10, okay? So as soon as you see that number pop out and you see that it's much bigger than 10, we can say, yes, the data is normal. If it's normal, it means we can find a z-score. We can take the next step. So that's what we're gonna do. We're gonna take the next step. Now, we already have our P and our Q, so we've got that. The thing we need is the P hat. So we look up to the problem and we look what it's asking us about. So it says find the probability more than 70% have fungus. So that guy is the one we're interested in, so that's gonna be our P hat, 0.7 or 0.70, however you wanna write it. Okay. So let's find our z-score. So we're gonna go z equals 0.7 minus the original 0.67 all over the square root of 0.67 times 0.33 all divided by 320. Now, like I said, not hard to do this. So the idea here is that you start the way that we always do. If you start the way we always do and do the top first and hit enter, so 0.7 minus 0.67, boop. Nope, that's not the enter key. That is the enter key, okay? So top first and hit enter as always, and then divided by, and then second square root, and then 0.67 times 0.33 divided by 320. You don't have to do anything else, that's it. Okay, hit enter, boop. And I got 1.14. Okay, so you see how once you put that square root in the bottom, square root, you just type in and hit enter and you're done. So it's just top first, hit enter, and then divided by square root, doodly-doodly-doo, and hit enter again. So there's no extra parentheses or anything like that, okay, which is really, really nice. Okay, so what did I say I got? 1.14. And remember that this is a z-score, so because it's a z-score, we're gonna use 2 decimal places. Okay. Now the thing to keep in mind is that we're doing all of this so that we can plot this on our normal curve. So it means that we're looking at a graph, 1.14 is over here, and we want to find the probability it's more than that, so more than would be shading this way. Now remember that this is our normal curve, our normal distribution here, so if we want to figure out that area, we're back to our normal CDF. Okay, on our calculator, normal CDF, we're going to go from 1.14, comma, 10,000, right? Off until forever. So same button we've always been using. No difference there. The z-score is different, but what we do in the calculator, it's not. It's all the same because we still have our normal curve. So I got an area of 0.1271. Now remember, that's not an appropriate answer, so we say the probability that we are more than 70% is 0.1271. So the probability that more than 70% of toes have fungus is around 12.71%. Okay, now there's more percentages wandering around here, so sometimes the answers are a little bit uglier or not as clear, but that's why we want to make sure we label everything appropriately. Okay, let's look at another one. So I'm going to give you, the next one I'm going to give you the setup a little bit different, okay? So this one says, oh poo. I just erased it, but apparently we're still using our same 67% and that's it. So a fungus. This is just part 2. So this time it says find the probability a sample of 160 toes shows less than 68% have fungus. Okay, so apparently I'm not showing you another type of example, we're just doing another example of this just to kind of get it stuck in the old head here. Okay, now we're still using our original 67%, but we've changed our sample size. So in order to find normal, again, we need to do the n times p times q. Now this time our n is 160. Our q is, or sorry, our p is still the same. So our p is still 0.67. And if our p is still the same, so is our q, is a 0.33. But the 160 definitely changes. So the number is not going to be the same. So you go ahead and you plug this guy into the old calculator, and you should end up with something around 35.4-ish. Again, we don't really care on the rounding, not a big deal. We just care that this guy is greater than 10, so the data is normal. So we can do the problem. Now we need to find our z-score. So we're using our new easy peasy z-score. We start with the proportion, with the number we are interested in our problem. So our problem is interested in 68% or less than 68%. So we're going to start with a 0.68. We're going to subtract the original, 0.67. We're going to divide by the square root, use the 0.67 times the 0.33. But this time we're not dividing by 320, we're dividing by 160. So the problem is most definitely changed when the sample size changes. So let me show you again here. Okay, so 0.68 minus 0.67. And then immediately divided by, and then second square root, and then type that whole thing, 0.67 times 0.33 divided by 160. Okay, whole thing, boop, and then just hit enter. Remember, this is a z-score, so this has 2 decimal places. So even though it's in decimal, the z-score is going to be 0.27. So this is 0.27. So remember, that's z. That's your z-score. So if we look at our graph again, so I'll draw another example here. We know it's normal because we did this. A 0.27 would be over to this side. And which way are we shading? The problem asked us for a less than. So we're going to this side here like this. And again, we're back on the normal curve. So this is going to go right back to our calculator. You're going to do the normal CDF. But this time our lower boundary over there is going to be negative 10,000, right? Negative 10,000 all the way up to 0.27, and we get the probability that we are less than 68%. So again, if you plug that into your calculator, use your normal CDF. I got 0.6064. Hopefully that's what you got, and that will be our answer. Okay, look good? Getting that in your calculator? All right, now let's do a completely different example, and I'm going to show you a different setup on this one. Okay, so this one we'll go to the snail example. So this one said 18.5% of people eat snails. Again, totally made up. I have no idea. This time it says, though, that the data is normally distributed. Find the probability that in a sample of 80 people, more than 19 eat snails. All right, so like I said, a little bit different setup. We're still given an original value to start with at the top. This one says that it's normally distributed, which means we're good to go right off the bat with drawing our normal curve, aren't we? So on this one, we don't need to do the NPQ. The test has already been done because it says it there for us. So we're actually ready to just jump into the problem. So the first thing to do to jump into the problem would be to find a z-score. But that first part of the z-score is the p-hat. And we've got p, but we're not given a p-hat here. So before we're ready to actually start with the z-score, we need to find our p-hat. And so in this example, this is one where we have to create it ourselves. It says in a sample of 80, more than 19 eat snails. So to find p-hat, we're gonna go 19 over 80. So we gotta do a little calculation to start with. And remember, when we do this, we're gonna go with 3 decimals. 19 divided by 80. And I got 0.238. Now it does come out perfect, so if you want to go to 2375 because it's perfect, that's fine, but I'm just going to stick with what I said so that everybody understands, that this is perfectly acceptable. Okay, so p-hat is 0.238. Now we're ready to find our z-score. So we start with our p-hat, 0.238. We subtract that original. Remember, it's 0.185 now. Then we divide by a big square root, put the 0.185, the p. Now, if p is 0.185, what is q gonna be? So what's the complement of 18.5%? Okay. Would it be 81.5? So 0.815. And then this time we're dividing by our sample size, but now we've got more numbers in it. Remember that this guy is our sample, so divided by 80. So try this one on your own. Remember to hit enter after the top, divided by square root. And hopefully you will get the same thing I have gotten of 1.22 for a z-score. So one more time, let's go to our graph, which we know it's okay to draw because it said normal in there. If here's the middle, a 1.22 is over here. Now be careful let's see, we want that more than 19 eat snails. So this is a more than problem. So we're shading this way. And then we need to find that area, right? So back to our calculator with our normal CDF. And pause there for a second while you do that. When I stuck this in my calculator, I got 0.1112. So we can say the probability that more than, and we can either write it with that or we can say more than 19 eat snails, and just write out what it actually asked us, is 0.1112. So there's an 11.12% chance that more than 19 of these people will eat snails. So if 80 people are coming to your barbecue and you decided you're gonna make snails, should you plan on everybody eating snails? Because even if it's just even 19 people, it's not that high a probability, right? So it's a low probability that people are going to eat snails, right? In my world. Okay, so that's how the central limit theorem works for proportions. So again, we have that new test, the NPQ, and then we have our new easy peasy z-score. So put that easy peasy z-score down as one of your formulas because we're going to use it plenty. So definitely get that guy worked out so that you understand how to plug it in your calculator and get the correct answer, and you'll be good to go. Alrighty, that does it for today. See you next time.